Welcome back. We will come to our second section, linear algebra. Since we all know linear algebra is an essential theory from the last section, we will learn it more in detail. First, let's check the basic concept and operations. Then we will learn the advanced parts like the linear transformation and the metric decomposition. It is known that the fundamental entity in the data management is the relation. For example, we need to implement some operations on relations like select, project, and so on in the SQL. However, the fundamental entity in AI and the data mining is the matrix. That's why we need to learn more about the matrix to do some applications. Linear algebra mainly deals with the linear problems, no matter in which form it expresses, scalar, vector, and metric. The scalar is a real number like x equals to 3. It can be completely described by its magnitude alone. Vectors are quantities that are described by both a magnitude and a direction. Let's see an example here, the vector x, in which numbers are arranged in order. Metric is the numerical table of n rows and n columns. The subscript of each element denotes the position. For example, the A11 means the first row and first column. The A21 means the second row and first column. The first number is for the rows and the second is for the columns. Each row or column represents one object. If rows are objects, then columns are features. If n equals to n, then the metric is a square metric. Before we get to the metric operations, we need to check the difference between the numbers and the matrices. Like numbers, metric can do addition, subtraction, multiplication, and division. Also, metric can be factorized to get the data patterns. This is called the singular value decomposition, which we will cover the details at the last section. Here, let's see the metric operations. When we do the metric addition, we need to make sure the two matrices are the same size, and then add their corresponding elements one by one. For the scalar multiplication, we should use k multiple all the elements in the metric. In terms of the metric multiplication, we need to make sure the number of rows are the same of the number of the columns in metric B. For example, we have two matrices A and B. And then we multiply the elements in metric A by the elements of each column in the metric B and add the products like so we get the result C is Here is an example of AI task, linear classifier. Let's see how we use matrix to do basic operations. To build a model to classify images in different categories. For example, car, cat, or human. We use 6 pixels, the vector x, to represent the image for simplicity. And we have the weight w and the bias b, which follows this formula, y equals to wx plus b. Here, the first row of the matrix W multiplied the vector x 10 by 10, we can get the 1.5. Then we need to add the bias b minus 1. Then we can get the 0.5. And the rest 2 rows are do the set operations to get the corresponding results. We can see the result of the cat 3 gains a higher probability, so we classify this image into cat category. This is a simplified case because in the real world, it will be much complicated. Apart from images, there are lots of different data types like text, networks, and so on. So how can we represent data? Normally, we can use the matrix to do this job. For the network data in the figure, there are 4 nodes connected, A, B, C, D. We can mark each connections between nodes as 1. Then we can get the matrix on these connections. For example, the node A connects the node C and node D. Then we can see the corresponding positions AC and AD are marked as 1, same as other nodes. So how about representing the text? For example, we have 3 documents that involve 4 letters, A, B, C, D. Then we can mark the frequency of each letter in each document. The first row represents the document 1. A is counted 4 times, and B is counted twice, C is twice. So we can see the result in the first row is 4220, same as other rows for the documents. Above are the representations of different data types. We use different matrix to store information. But how do we compare the difference between the different objects? Normally, we use 1 row or 1 column in the matrix to represent 1 object. In other words, we need to use the vector to compute the similarity. Suppose we have the vector x and the y. Both vectors are in n dimensions. First, we do the dot product of x and y. Then we calculate the norm of each vector. And last, we calculate their similarity by this formula. On this page, we will learn determinant. Different from matrix inside brackets, determinant represented in several ways. Normally, it is signified by 2 straight lines. There are 2 main differences between matrix and determinant. Matrix is a combination of factors. The determinant is a scalar value that can be computed from the elements of a square matrix. It encodes certain probabilities of the linear transformation described by matrix. For the detailed calculation for 2x2 metric or 3x3 metric, we can refer to those two formulas. Here is an example for determinants. Suppose we have two vectors, A and B, and we can get the determinant 3 by the formula. 3 indicates the yellow area in this picture.